So our discussion today is going to focus on two topics in particular. The first thing we're going to look at is molecular polarity. And the second thing that we're going to look at is more of a construct of how all of this goes together. So thus far, and by that I mean over the past 2 weeks, we've mostly focused on kind of answering the question of what. What does a molecule look like? How is it put together? What kinds of bonds are in a given molecule? What kind of shape does it take on? What are its bond angles? The last thing that we'll talk about after polarity is going to answer the question of why or how. So, how does an atom turn into a molecule? How are all of the bonds made? That's going to be the primary focus of the last piece of this, which we'll get into in a little bit here. But let's finish off this idea of polarity before we get into that. So with polarity, what we are looking for is something called a dipole moment. Dipole moment is basically a description of an unevenness of sharing in the electrons across an entire molecule. So we've talked about the idea of bond polarity in the past. I've got an atom of oxygen and an atom of hydrogen. I can look at the electronegativities of each and determine that since the oxygen is more electronegative, the electrons are going to spend more of their time over with the oxygen. That much we've seen so far. But that really doesn't tell the full story if we start to go from just an individual bond to an individual bond that is part of a larger molecule. So for dipole moment, what we are looking at is what is the overall polarity of a given molecule? Is a molecule polar or non-polar? And for that, your book talks about the idea of magnitude and direction. Magnitude being how polar is the bond that we are talking about. Direction being what direction does the polarity go? And so we will see in these kinds of evaluations, we'll see notation like this. One type of notation that we will see is one of these funky looking arrows. And what the funky looking arrow tells us is it gives us a directionality to the electron density of that bond. So here at the crosshairs, which kind of looks like a plus sign, we are going to find fewer electrons. And so we sometimes will denote that as slightly positive using the lowercase Greek letter delta to indicate that partial positive charge. The arrowhead side of the arrow indicates the area where there is a greater electron density. And so we would signify that with a lowercase Greek letter delta minus to indicate that that area contains a partially negative charge. Now, your book takes this concept of a bond dipole and this idea of a net dipole moment, and I think makes it maybe a little bit more complicated than we need it to be. Because it talks about vectors and magnitude and diagrams. And if you're not an engineer or a physics student, you probably haven't seen a whole lot of vectors and that kind of diagram. I want you to consider one word for today. We're going to call it our keyword. And the keyword for today is symmetry. What does that mean? Well, when we're looking at symmetry, that's what we're looking for. Symmetrical molecules tend to be nonpolar. So in the case of carbon dioxide here, carbon dioxide is a great example of this. I've got polar bonds. Those polar bonds are pushing the electrons in equal and opposite directions. So even though there is a great polarity, I can see that the oxygen atom has a lot more electron density around it than the carbon atom does. Even though that is the case, and that is true, carbon dioxide has a net dipole moment of 0. It's completely nonpolar. Why is it completely nonpolar? Because all the electron density that's pushed toward that oxygen on the left is matched by an equal amount of electron density being pushed to the right. And so no matter how I look at this molecule, there is no way that I can separate the positive side from the negative side. Even though it is made up of polar bonds, those polarities have been diffused and spread out in all directions. So there's no net congregation of electrons on one side of the molecule compared to the other side. So when we're evaluating polarity, the word we need to think of is symmetry. Is this molecule symmetrical? Because if it is, we can automatically tag it. It's nonpolar. If it is not symmetrical, then we can look at it as being polar, and we can answer a few other questions about things like which side is the negative side, which side is the positive side, or as your book says it, which direction does the net dipole moment point? So let's take a look at some key examples here and try to make some sense of it. So I'm just going to drag these keywords up here. So I'm looking at boron trifluoride. So I'm going to also use model kits here just to kind of help us with that. Boron trifluoride, I've got a steric number of 3, and I've got the same bond going in all 3 directions. Just like this. The question we would ask ourselves, we know that the boron to fluorine bond is polar. There's a great electronegativity difference between boron and fluorine. Is the molecule itself symmetrical? Yeah. All 3 positions in this trigonal planar shape are all occupied by the same kind of bond. This is symmetrical. As a symmetrical molecule, the net dipole moment, 0. It's nonpolar. If I look at this from a different perspective, let's take a look at carbonyl sulfide, COS. Here I have a steric number of 2, a linear shape. If I have oxygen on one side and sulfur on the other, couple of things here. First of all, I can tell just from looking at this that there is a lack of symmetry. I've got a different atom on the left-hand side in the sulfur compared to on the right-hand side in the oxygen. I know that just by looking at it. So from that standpoint of symmetry, I would already evaluate this as being polar. If I dig deeper into the bonding, I could also look at this and say, well, carbon and sulfur have the same electronegativity. So that bond between copper and sulfur, not copper, carbon and sulfur is nonpolar. So I've got a nonpolar bond in one direction and a polar bond in the other direction. The net direction of polarity is going to be toward the oxygen atom. That's what they call the net dipole moment. But let's just imagine for a second that this wasn't a nonpolar bond. What if it was a polar bond also? What if it was carbon being bonded to nitrogen instead of sulfur, where we would have a definitive value for that bond? The fact that the electronegativities are different on each side does make a difference. This bond is more polar between carbon and oxygen than this bond on the other side. So even if electrons are being pulled in both directions, if they're not being pulled evenly in those both directions, there's still going to be a lack of symmetry. There's still going to be an overall dipole moment. I want you to think of polar bonds as kind of like a subatomic tug of war game. In this particular example, I've got a bodybuilder representing oxygen pulling the electrons to its side, and I've got a kindergartner on the other side pulling electrons over to its side. Probably doesn't take a whole lot of thought to know which way, who's going to win that tug of war. Bodybuilder versus kindergartner, I'm going to take the bodybuilder. And that's the direction that the electrons go. So again, it's more important to think about things from a symmetry standpoint than it is from even a polar versus non-polar standpoint. Symmetry is always going to win out. If it's not symmetrical, it's polar. Let's take a look at a couple of other examples. Here I have phosphorus pentachloride, PF5. We've seen this one before. One note I want to highlight to you is this. When we start getting into these advanced shapes, so we're talking steric number 5, steric number 6, where we've got this whole axial versus equatorial thing going on. In those cases, we have to evaluate symmetry just a little bit differently. We almost have to break it into two different pieces. We need to look at axial symmetry and equatorial symmetry. And we want to evaluate them individually from each other. So in the case of PF5, from an axial standpoint, I've got the same atom. I've got fluorine on top and fluorine on the bottom. So that's symmetrical. In the equatorial, I've got fluorine in all three positions. So that's symmetrical. Symmetry in the axis, symmetry in the plane. This is a symmetrical molecule. If it's symmetrical, it's nonpolar. And so what we see here, net dipole moment, 0. Now let's take a look at that circumstance here. What if one of those fluorines gets replaced by a chlorine? Well, in that case, we have something different going on. So let's take a look at the first example. Example A, chlorine in the axial position. Well, in this circumstance, the equatorial plane is still symmetrical, but the axis is now not symmetrical. That is an element of asymmetry. As an element of asymmetry, what are we going to see? We're going to see polarity. What direction is the polarity going to point? Well, in this case, chlorine is less electronegative than the fluorine is. We're going to see a net direction toward the fluorines and away from this chlorine. So the net direction for the dipole moment in this case would be up in the opposite direction of the chlorine. If the chlorine was in the equatorial plane instead of in the axis, same thing. Now I have axial symmetry, but I lack symmetry in that trigonal plane. So what do? Well, I know that this is electronegative as the chlorine compared to the fluorines on the other side. That lack of symmetry creates polarity. What does that polarity do? Well, it's going to push in the opposite direction from that less electronegative atom. So once again, the key word here, symmetry, helps us to dictate the idea of polarity. When things are symmetrical, they are nonpolar. When things are not symmetrical, they are polar, and we can usually identify the direction of the polarity by evaluating kind of how that asymmetrical piece impacts the electron density. Right, any questions so far? Okay, so let's get into our first question for today. We have dichloromethane, CH2Cl2. We know it's polar. You can tell right away. It's asymmetrical. The question is, what direction do we find that electron density going? What direction is the dipole moment going? Now, quick note about this one, you can select multiple answers here. So make sure that you're describing all of the directions that electron density can go. All right, so if this is my molecule, somebody give me one of the directions that the dipole moment is going to point. Okay, down is one of the directions. How do we know that? Again, if we're looking at the center atom as a reference, the chlorine, which is more electronegative than the hydrogen, the chlorine is below the center atom. So down is one of the directions. Is there another direction? Yeah, right. So both of these chlorine atoms are to the right of the center atom. So the net direction would be down and to the right for that dipole moment. Front and back, well, they're canceled out. This one pointing forward is going to be canceled out by this one pointing backward. So down and right would be the two answers here that we're looking for. All right. Let's move on to some practice problems. Now, these practice problems that I'm about to show you, these are the same practice problems that were featured in that supplemental video. So I'm not going to go through the process of how to draw them. What I'm going to give you instead is what the drawing looks like and can we evaluate their polarity based off of that drawing. So you're still having trouble with drawing and making three-dimensional structures, go back to those videos and pick up more from those. So we're starting out here with selenium tetrachloride. Selenium tetrachloride had a structure that looked like this. Steric number of 5. This is a seesaw configuration. Question is this: is this molecule polar? So what's the key word today? Symmetry. Is this molecule symmetrical? One important note to remember: since we are talking about one of the advanced structures, in this case, we're talking about trigonal bipyramidal, we have to evaluate symmetry in the two different dimensions. So from an axial standpoint, is this symmetrical? Yeah. Chlorine above, chlorine below. Axially, it's symmetrical. Is it symmetrical from an equatorial standpoint in that trigonal plane? That lone pair there is not the same as these two bonds. There's our element of asymmetry. So from that standpoint, we know that this is polar. It's polar because we've got this asymmetrical piece right here. Now, this question wasn't asked, but we're going to ask it anyway. What direction does the dipole moment go here? Right. This is where lone pairs are a little bit different, and we need to take them into consideration here. So, is this lone pair being shared by anything? So where's the heaviest electron density? Where it's not being shared. So our net electron density is actually going to be right here around this lone pair. That's going to be our center of polarity here. So this is the negative side. This ends up being the positive side as a result. Triiodide ion. Now, the triiodide ion also fits into this trigonal bipyramidal framework. where in this case, I have 3 sets of lone pairs in that equatorial plane. All right, let's talk a little bit about symmetry. Is this molecule symmetrical? Okay, remember, 2 different pieces. Is the axis symmetrical? Yeah, iodine above, iodine below. Is the equatorial plane symmetrical now? Yes, lone pairs in all 3 positions. So I've got axial symmetry and equatorial symmetry. The whole molecule is symmetrical, even though I've got a combination of iodines and lone pairs here. All the lone pairs cancel each other out. All the iodines cancel each other out. This is nonpolar. Any questions with either of these 2 examples? All right, I'm going to ask you then to try out these 4. And so, yeah, I'm not going to ask you to draw them. I'll draw them here for you to look at. So PSCl3, this is a tetrahedral. IF4 minus is square planar. IF4 plus is seesaw. And nitrite ion is bent. All right. With the person sitting next to you or somebody nearby, just talk out these 4. Tell and figure out, are they polar or non-polar? Don't worry about assigning direction of the dipole moment. Polar or non-polar. I'll give you, let's say, about 4 minutes. 1 minute per structure. Hopefully it doesn't take that long either. All right, looks like we're on the right track. So in the first one, we have an element of asymmetry in the form of this sulfur. So that asymmetry would make it polar. In the second one, now, if you didn't draw it correctly, you have problems with this. But in the second one, you should have come up with symmetry in the axis because the two lone pairs cancel each other out, and symmetry in the plane because the four fluorines cancel each other out. So each dimension was symmetrical on its own. We don't need to compare symmetries of the axis to the plane. That's not part of this. So this is nonpolar. In the third one, this is very similar to the PF4 that we were looking at before, or the PCL. This one, we've got an element of asymmetry from that lone pair, so this is polar. In the last one, same thing. Lone pair gives us that element of asymmetry. The nitrite ion is polar in addition to being ionic. Right. Any questions about polarity? Charles. How do I get the first one? Okay, so we've got a tetrahedral here. So we've got sulfur in a position instead of a chlorine. That's your piece that is different. Remember, any piece that is different is going to create polarity of some kind because you're going to have a difference of electronegativity. So with sulfur being less electronegative than chlorine, it's that tug of war. You've got the strong man against the child in one example, or in this example, I guess it'd be a strong man against a normal man. Because sulfur is not that much different than chlorine. But there'd be enough of a difference that you'd see those electrons being pulled down toward that chlorine. You would see a net dipole moment. Doesn't matter. Electronegativity is the only thing that matters there. Now, if we want to start getting into double bond versus single bond stuff, that's where the mechanics piece that we're about to get to actually takes off. So what we want to start talking about now is the how and the why. Well, the how and the why. So thus far, we've been more concerned with the idea of what is the structure and what is its shape, what is its bond angle, is it polar? And we really haven't focused at all in terms of how does it come together in the first place? Why do these bonds ultimately form? How do they form? And when we start trying to get into that question, we start to have to ask ourselves really difficult questions along the way. For example, most of the orbitals that we have talked about in the valence shell have either been S or P. Now, if they're going to share electrons, in some way or another, they are going to have to be able to touch each other, right? The problem becomes, how close do they have to get to each other to touch each other? Now, in some instances, that's not a problem. So if I have one orbital that is arranged like this and another orbital that is arranged, I can see that if this black ball in my model is the nucleus of my atom, I can get these two orbitals to touch each other and not really have to worry about how far apart they are from each other. And if I want this orbital to touch this s orbital, again, not too big of a deal to do so. But the problem is, this is only one orientation of a p orbital. The other three orientations, or the other two orientations rather, are not nearly as conducive to that kind of touching. If I have an orbital like this, it becomes a lot harder for it to get to that s orbital. They have to get a lot closer to each other to do it. If I have the orbital that looks like this, they got to get a lot closer to each other to do it. I start running into repulsion issues where now those nuclei are a little bit too close to each other and start pushing each other away. So we start to run into a problem here of distance and orientation. How do I get this to work? And so what we have to understand is that the way that we have viewed electrons up until this point, in terms of atomic orbitals, s orbitals, p orbitals, d orbitals, f orbitals, and so on, that works great if we are talking about that element in its atomic form. When that atom starts to undergo a chemical reaction to form a compound, it doesn't stay in that atomic arrangement. Those s orbitals and p orbitals and d orbitals, they have to change in order to allow that molecule to form. And so there are a number of models that exist to try to explain this. Some of them go way deeper than what we want to. The one we're going to focus on is something called hybridization. Hybrid orbital theory describes the transformations that take place inside of an atom to allow that atom to turn and bond with another atom. Generally speaking, we're talking about the valence level. So we're talking about s orbitals and p orbitals and how those s orbitals and p orbitals kind of fuse together to create the molecular shapes that we've been talking about. So everything that we are going to describe in this section relates directly back to what we've already talked about and drawn and elaborated on in terms of bond angles and in terms of everything else. It's just a matter of trying to connect the dots to figure out how it actually happens. One other piece of information for us before we go into that further concerns the idea of bonding. So that kind of bonding that I was talking about, those orbitals touching each other, that's called direct overlap bonding. Direct overlap bonding, or head-on overlap, is a characteristic trait of what is called a sigma bond. Now, sigma bonds exist in all chemical bonds. Every bond that exists between two atoms starts with a sigma bond, because I have to have that direct overlap between the two atoms to get them to be attracted to each other and stay attracted to each other well enough before I can do anything else. So from that perspective, any single bond is a sigma bond. But really the way we want to kind of frame it and phrase it is that all bonds start with sigma bonds. And what that means is If there are bonds in addition to that single bond, in addition to that sigma bond, they can exist too, but they exist in what are called pi bonds. Pi bonding is the result of indirect overlap, side-on overlap. You see this taking place primarily between p orbitals that do not go through hybridization. So if I take a look at two models here. If I have two p orbitals that are oriented in the y direction like this, side-on overlap would be the interaction of these orbitals above and below the nucleus. Now, why can't this happen on its own? Well, this is exactly what we were talking about. This is a repulsion thing. If I was trying to get them to engage each other just in this way, the repulsion between the two nuclei would be too much. It would drive them apart. But if a sigma bond has already been established and there's already an interaction between them, a pi bond like this can come in and insert itself to give a double bond if there's one pi bond, or a triple bond if there are two pi bonds. So we only see pi bonding taking place if there's a sigma bond already in place as well. So pi bonding comes in mostly in multiple bond situations. So if I was going to describe that double bond there between the carbons, I would describe it as a sigma bond and a pi bond. Two bonds in total. One sigma, one pi. That's where we're going to leave it for today. So on Friday, we'll get into these hybridization schemes. We'll talk about how we go from atomic orbitals with electron buildup to hybrid orbitals that actually go out and do the bonding. It looks a lot worse than it actually is. But as you're going through that skill builder over the next couple of days, one thing that is really important that you should note, these all tie back to steric number. So if I know the steric number, I know the number of hybrid orbitals. If I know the number of hybrid orbitals, I can piece together what that looks like by simply counting. So I need 4 orbitals here. S2 gives me 4 orbitals. It's the s orbital plus the 3 p orbitals in that valence shell to give me the 4 orbitals I need for tetrahedron. If I had fewer orbitals needed, I would pull in fewer from the valence shell. I always start with s. It's just a matter of how many p orbitals I need to do that. So that's Friday. No stoplight questions for today. I'm going to save that for the end of the whole thing on Friday. Have a good day.